Section 7.1, Trigonometric Ratios and Radian Measure. So the first section, Trigonometric Ratios, is just revision from Year 10. Think about a right angle triangle. Opposite the right angle, we'll have the hypotenuse, which is the longest side length. If we're involving a particular angle, and in this case it's just an unknown angle theta, then opposite that angle theta will be the opposite side length. And next to that angle theta will be the adjacent side length. So whenever we get a trigonometric problem, it's always a good thing to start by labelling the side length. So opposite the right angle, hypotenuse, opposite the angle, opposite, and then of course that leaves us with the adjacent. Now here's the thing, sine of the angle theta will equal the opposite side length divided by the hypotenuse. So that's the SO part of SOHCAHTOA. Cos of angle theta will equal the adjacent over the hypotenuse. So cos of that angle there will be equal to taking the adjacent and dividing it by the hypotenuse. And finally, the TOA part of SOHCAHTOA is tan of the angle will equal the opposite side length divided by the adjacent. So here we have the angle. If we take the tan of that on our CAS, it will spit out a certain number, and that will be equivalent to taking the opposite side length, dividing it by the adjacent. We also have some basics about angles of depression and angles of elevation. Let's consider that we're at this position here on a cliff top. If we look down into the ocean to see a ship, then what we are doing is from the horizontal, moving our eyes down an angle of depression to sight the ship. If we now take this perspective again, we turn around and we look up into the sky to see an aeroplane, then from the horizontal, we lift our eyes up an angle of elevation to see the aeroplane. So angle of elevation and then angle of depression. Let's look at a couple of examples here. So in problem A, we have 64 degrees, we have a hypotenuse, and we have an unknown adjacent titled x. So we're involving an angle, an adjacent, and a hypotenuse. So obviously this is going to be involving cosine. So cos of 64 degrees will equal the adjacent over the hypotenuse, and then we can just solve for x. Now you can either use NSolve on your CAS if you've been shown that from Year 10, or you can just simply look at that equation there, multiply both sides by 9 to get x. Either way you want to roll. For B, this time we have an unknown hypotenuse, we have a known angle which is 27 degrees, and we have an opposite side length. So this time we're going to be involving sine. So sine of 27 equals 4.1 over x. Again, just solve for x. And finally, we've got an unknown angle, x. We have a known opposite and a known adjacent. So tan of the unknown angle x is equal to the opposite over adjacent. Solving for x, and we get 48.9 degrees. So you can use the solve function or the NSolve function on your CAS, or you can just go inverse tan of 8.6 over 7.5 to get out that 48.9 degrees. Now in this particular unit, you're going to be using two methods of measuring an angle. So we're going to have a radian, and we're also going to have what you're used to being degrees. So in this particular setup, it just shows you how you'd move into degree mode or ensure that you're in degree mode. So you just want to go into your settings, and then your document settings, and then look for the angle, and you either nominate degree or radian, and you can make that your default, or you can just make it the setting for that particular document that you're working in. But you are going to have to go back and forth at the beginning, but towards the end of this unit, you're going to be working in radians, and you'll do the same thing next year at Year 12. When we measure the length of something, you'll probably be familiar with two different types of systems. We can have feet and inches, or we can have centimetres and metres. So there's two different systems there that we use for length. The same thing applies for when we measure angles. And so far what you've been used to doing is measuring angles in degrees. But there's also another system known as radians. Now, why did we use 360 degrees to represent the angle that we cover in a full circle? Often when we're involving a circle, we're interested in the different fractions of the circle that we have. Now, 360 has lots of multiples in it, lots of factors. So, as an example, if I wanted to have a quarter of a circle, I could represent that as being 90 degrees. If I wanted a third of a circle, then it would be 360 divided by 3, which would be 120 degrees. If I wanted half a circle, I would have 360 divided by 2, which would be 180 degrees. If I wanted an eighth of a circle, you get the idea, it would be 360 divided by 8, which would be 45 degrees. So in that way, to represent different fractions of a circle, the 360 degrees in a full circle makes a lot of sense to us. But what about a radian? What does that mean? Let's look at this diagram. We have a unit circle here, so that just means that we have a circle centered at the origin with a radius of 1 unit. So the radius here is 1. A radian is the angle swept so that the arc length, the length of the curved section, is equal to the radius. So from the origin to the outside of the circle is 1. Now if I take this point and sweep around, I keep on sweeping until this part in blue is also equal to 1. When that's achieved, I say that the angle in the middle is equal to 1 radian. So if you think about it, if the radius was equal to 5 and I swept around 1 radian, an angle of 1 radian, then the arc length would also be 5. So looking at this unit circle where the radius is equal to 1, if I do 1 full revolution around the unit circle, I have created an angle of 360 degrees. Now what is that equal to in terms of radians? Well, if we look at the circumference is given to us as being 2 pi r. Now in this unit circle, the radius is 1. So the circumference becomes 2 pi times 1, which is just 2 pi. So the angle that we've swept by beginning at this point and going all the way around the outside in radians is equal to 2 pi. So what we can come up with is that 2 pi radians is equal to 360 degrees. Note that the degrees has that little 0 up the top and the radians has that little c. If we don't see a little c or a 0, then we assume it's in radians. But this is the basic equation. 2 pi radians is equal to 360 degrees. 1 full revolution of the unit circle in either format that you're using, radians or degrees, should be equal to one another. I can divide by 2 and come up with that pi is equal to 180 degrees. Now if I'm after 1 radian, I know that that's going to be equal to 180 divided by pi degrees. We can also use that to work out what 1 degree is equal to. So this time 360 degrees is equal to 2 pi radians. I can come up with that 1 degree is equal to pi divided by 180. So this is the critical part. If we are going to be converting from degrees to radians, then we simply take the angle given to us in degrees and multiply it by pi on 180. And if we're going from radians and converting to degrees, then I simply take the radian angle and multiply it by 180 over pi, and that will convert it to degrees. We also have another rule, which involves the arc length. The arc length will be equal to the L here, the length of the arc length. It will equal the radius multiplied by the angle that we've swept through. But this angle needs to be in radians. And you'll see some examples of that being used. This is just for reference. I don't expect that you are able to regurgitate that off by heart right now, but as you become more and more familiar with working with these kind of circular functions, then this will become more automatic for you. But you don't need to be able to commit that to memory just now. But we have the critical angles that are given in radians around the inside, and then those same equivalent angles shown in degree format around the outside. Let's look at some conversions. Convert the following into degrees. So I've got 6.3 radians. What's that equal to in degrees? So it's 6.3 multiplied by 180 on pi. And I literally put that part there into my CAS calculator, and that pi, of course, is equal to 3.142, and I put that into my calculator using the pi button. So you go 6.3 times the fraction, 180 over, and then you insert the pi button there, and it'll spit out 360.96 degrees. Here we have 9 pi on 10. Notice that this time there's no little c there. So we make the assumption that that angle is in radians. So 9 pi on 10, converting that into degrees, I just need to multiply by 180 on pi. So it's 9 pi times 180 to give me that, and 10 times pi to give me this. The pi's cancel, and the 10 goes into that figure there exactly 162 times. So 9 pi on 10 is equivalent to 162 degrees. Working the other way, converting 36.35 degrees into radians. So 36.35 multiplied by pi on 180. Again, use the pi button, and we spit out 0.63 of a radian. And I need to show that as being radians with that little c. What's 150 degrees equal to? So 150 multiplied by pi on 180. Now, if you can, maintain the use of the pi, all right, because that's more exact than when we round. So I've got 150 times pi on 180. So just think of 150 as being 150 on 1. So multiplying your fraction through, I get 150 pi on 180. And at this stage, what I should do is divide both the top and the bottom by 10 to get 15 pi on 18. So that's a mistake there, having a 6, it should be 18. And if that was an 18 and that's a 15, then obviously 3 can go into both. And it goes in 5 times at the top and 6 times down the bottom. So 150 degrees is exactly equal to 5 pi on 6. And that's an exact format. I don't need to put that little c there to show that it's in radians. The assumption should be that if you have an angle expressed with a pi in it, that it automatically is in the radian format. Now we're going to be making use of the arc length rule for problem 3 here. So find the exact length of the arc formed by the angle of pi on 3, so there's my angle, and that automatically is in radians, in a circle of radius 6 centimeters. So for A, theta in radians is pi on 3, the radius is 6. What's the arc length that would create by sweeping through that angle if the radius is 6? There's my rule, sub in, and I end up with 6 pi on 3, which is equivalent to 2 pi centimeters. So that's the exact format. That's approximately equal to 6.28 centimeters that you generate with that arc length if you swept through that angle. B, what's the angle that would create? Subtended just means created there in between those two. Given that, or swept through is probably a better word, if the radius is 5.4 centimeters and the arc length is 3.5. So let's write down the info that we know. So R is 5.4, L is 3.5. Here's my rule, sub in the knowns. What I don't know is this angle. And if I solve for that angle, I'll get 0.67, and that's radians, because our angle always involves radians for this rule. C, find the exact length of the arc formed if the angle is 45 degrees and the radius is 2. So firstly, let's convert into radians. So I've got 45 degrees, and you can see that that's equivalent to pi on 4. The radius is 2 centimeters, so I sub in the stuff that I know, and I work out that my length is pi on 2. and that should be centimetres because that's been given in centimetres. So just put that centimetres in there in your notes. So it's pi on 2 centimetres. So that's 3.142 blah, blah, blah divided by 2. So you're looking at, about 1.5. But give the exact format if possible. All right, a little bit of an application of that rule. The minute hand clock is 15 centimetres long. If the end of the hand travelled 10.5 centimetres, so if it's travelled the end of the hand, that's the arc length given to us. Through what angle to the nearest degree did the hand rotate? So the arc length is 10.5, R is 15 centimetres, and the angle swept is unknown, but that angle will be in radians. So L equals R times theta, sub in the knowns, and we work out that theta is equal to 0.7 radians. Converting to degrees, because that's what the question requires, 0.7 radians is equal to 0.7 multiplied by 180 on pi, and we get exactly 40.1070, which is approximately equal to 40 degrees when we round it to the nearest degree.